Okay, so I want to talk about this lovely arrow category. Um, so this is this is a category of pre-sheaves. Here's an example picture of one of the objects of its category, and it can also be visualized like this. So it's a mapping from one set to another set. So the target set we typically call the vertex set, x of v. And we draw dots or vertices to represent those. And then the source set we call loops, the elements loops. So these are different loops on these vertices. Now, basically the idea here is that, the formal view is that these objects are functors from the opposite of this category to set. Okay, so x of p here becomes the update function. Now, in sort of correspondence with the Yoneda lemma, we want to really talk about what's going on in terms of arrows from these Hom functors, because we can talk about everything in terms of those. So we have two Hom functors, the Hom functor h of l, objects of which are Hom blank comma l. So for example, so Hom h subscript l or Hom blank comma l, it's another functor from COP to set, and the way it works is that, for example, HL of V is the set of arrows in C from L to V, so it just contains P. HL of L is Hom L of L, it just contains ID of V. Okay, so this Hom functor looks like this kind of function and basically just corresponds to a loop. It's actually also terminal object. It's actually also, a point, but it looks labeled differently here. The other Hom functor, the other kind of fundamental particle in this universe of arrows, is h of v, and that just corresponds to a single dot with no loops. And so stuff can be referred to. We can refer to the loops in a general kind of bouquet. These things are also called bouquets, and in a general bouquet or function, we can refer to the loops as arrows from HL. We refer to the dots as arrows from HV, and there's also this kind of, you could say it's a natural transformation from this Hom functor to this Hom functor, but basically it's just this kind of finding the dot of a loop kind of operation, which is called HP. Now, the one really magical thing about this arrow category is that there's a sort of switch operation. Now, I don't know if this is well known. I don't know what it's called. It seemed like such a powerful idea. I'd imagine if it has been discovered, it'll probably have some name. But basically, the idea is that if we consider have we got a general example here? No, I'll go back. Let's find a general example. Let's go back to here. Scroll down. Whoops. General example. Okay, here's a general example. So say we have a morphism from one of these, I'll just call them, one of these objects in our category. let's call it the category of functions, okay? And let's call these functions, or sometimes bouquets, okay? So okay, we have a morphism from this bouquet to this bouquet, and it's I mean it's indexed by alpha and beta. So there's a function alpha from A to C, and there's a function beta from B to D. Now, the interesting thing is that we can get this sort of morphism, and we can kind of switch it to become another morphism. So we can then form this object A arrow alpha C, that's another bouquet, and B beta to D, that's another bouquet. And the F and the G here that used to be part of these old bouquets now form a morphism from this to this. And this type, and then of course you can switch back. So you could say that this is a involutive covariant endofunctor of the arrow category of sets. I mean, that's what it corresponds to. But I mean, that's a bit of a complex way of saying it. And indeed, this kind of thing would hold when you get arrow categories of any category C. But the interesting thing is what it infers, because, for example, if we consider, and there's lots of nice cases, but one sort of fairly interesting case is if you consider a sort of endomorphism of one of these bouquets, so indexed by alpha and beta, that actually corresponds to a we actually get the sort of loop assignment function from that bouquet, and we get a pair of them, and those become, I mean, you can really think of this as like an update function in the category of dynamical systems. So we get this connection with dynamical systems. And indeed, if you let alpha and beta, if you let A and B be equal and F be the identity, then we see that an endomap of a sort of discrete bouquet is just a dynamical system. So there's lots of very interesting things, and all of these interesting connections. There's more. Another thing you can do is set the loop set to be empty. Then you just get these kind of things, and then there's all these special cases. In fact, there's something else which I noticed that I haven't elaborated on yet, but I should probably explore it at some point. But there's a version of this result for graphs, actually. If you have a pair of graphs and then you have a pair of morphisms, parallel morphisms from graph X to graph Y called alpha and beta, again, you can do a switch. So those morphisms then form graphs, and you can actually decide which morphisms represent the sources or the edges. So there's there's two directions ways of doing this. But then the old source and edge assignment functions become morphisms between those pairs of graphs. So, I mean, this is a very interesting kind of thing, I think. And as I say, I don't know if this has been discovered. I imagine it has, but I don't know. Anyway, let's get on with there's all this interesting stuff about switching. So here's a nice picture then of how we can refer to this stuff. So we have Yes, h of p after that is just that after hp is just its vertex. Yes. So yeah, basically, consider a bouquet X. Say we want to refer to this this loop at the bottom here. Well, we can do that just by actually talking about the loop, as a member of the set X of L. Or we can, probably more elegantly, we can refer to it as a morphism from this single loop hom functor here. And if we want to find the dot on that loop, the vertex of it, we can just take that morphism phi and do phi after h of p, and that'll give us this green arrow, which will just point to the actual dot. Okay, so we can talk about all the stuff in terms of arrows, and I kind of flip-flop between the two in this. So anyway, my task has been to compute the exponential objects of these of this category. Why? Well, there's already, as I've indicated with the switching thing, there's some fairly beautiful relationships. In terms of, for example, if you have an arrow, so a discrete bouquet is just where you have a load of dots and every vertex has dots. Every vertex has one loop. So essentially that's when the function in the bouquet, the loop assignment function, is the identity. Now if you have a morphism between discrete bouquets, you can actually think of that as a bouquet itself. Okay, because we have, for example, we have a discrete bouquet is going to look like this. Say we've got another one that'll look like this, and then we've got a morphism between them. So this is the traditional picture of it, but we can also draw it like this then. Well, alpha and beta will actually have to be equal, if you think about it. And so what it really boils down to, in the other view, is that it's this morphism actually becomes another object, another bouquet, and then this ID is just like an identity function of it. So we'd actually refer to the objects in our category, general objects, as morphisms between discrete bouquets. So there's already a very large amount of ways to talk about things. We can talk about them as functors, we can talk about them as arrows from the hom functors, we can talk about them as objects, and then when we have the exponential objects as well, we'll be able to refer to things as dots and arrows in objects as well. So the amount of sort of, I suppose you might call it self-reference or something like that, is just astonishing. It's yeah. And also it turns out that the problem of calculating the exponential objects is really, relatively simple. Exponential objects are extremely complicated in my opinion. especially when you do them in general. But I think this case of bouquets is one of the simplest, and things do simplify a heck of a lot. So, so here we go then. We're interested in finding the structure of the exponential object. So suppose we have a general bouquet x and a general bouquet y. We want to construct this exponential object y to the power of x. So it's going to have some vertices, I might call them dots sometimes, dots, and it's going to have some loops. So all we need to do is start with, at least, is find the dots and the loops. So a loop is going to be an arrow from HL, an arrow 5 from HL to y to the x. Now we know HL is basically just 1. So in other words, a point of a loop is going to look like this. And roughly speaking, that's going to correspond to a morphism from x to y. Why? Because we're allowed to take this x downstairs and put it here when we go from this adjoint thing to the original thing. And so, it's actually technically going to be a morphism from 1 times x to y. But 1 times x is isomorphic to x. So that's cool. We already know what the loops are. They're just morphisms. They're just morphisms from x to y. How do we actually compute all the morphisms, all the bouquet morphisms from bouquet x to bouquet y? That's actually going to become clear later. So we're going to get there. Now, the other interesting case is what are the dots of y to the x? So dots is going to be an arrow from h of v to the exponential object. It's going to correspond to an arrow from h of v times x to y. But h of v here is just a single dot with no loops. So all this does is it selects the vertex set of x. So indeed we find that a dot of y to the x actually just corresponds to a set mapping from the set of vertices of x to the set of vertices of y. And then if we do our switching trick, and we could say, well, this corresponds to a mapping from the discretized set, dots and loops on V, so on. And this just corresponds to a object, which is just the set map. So what I'm basically saying is that the set map just corresponds to an object of our category. So that's interesting. The dots of y to the x correspond to objects which are forming arrows from the vertex set of, from the vertex set of x to the vertex set of y. Okay. So then the next question is when will what are the loops on a given dot, or alternatively, given a loop, what will its dot look like? I mean, every loop just has one dot. And the answer is quite simple. Every loop corresponds to a morphism from x to y, and if we just look at how that morphism works on vertices, that corresponds to the kind of vertex map that the dot corresponds to. And given this, we can actually find out the loops on a given dot. So say we have a dot, this is in the exponential object, so that will correspond to a mapping alpha v from x of v to y of v. Well, then all the loops are just going to be all the functions from x of l to y of l, which complete this square here. And so, I mean, what you can think of this as is we have the structure of x fixed and we have the structure of y fixed, and we know how the vertices of x are getting sent to the vertices of y, and what we're asked to do is to map the loops of x to the loops of y to form a morphism. And so what you then have to do is whenever you have a vertex with some loops going to another vertex with some loops, you know, according to this alpha v here, you then just have to figure out a way to assign the loops of the source vertex to the loops of the target vertex. And that will correspond to, if you do that for every vertex, that'll make one of these alpha L's here, and that'll give you, and that'll correspond to, thinking about the exponential object, that'll correspond to one of the loops on that vertex. And then the what about the lone vertices and the sort of bald vertices of y to the x? Well, they just correspond to mappings from x of v to y of v, which are not part of any morphisms from x to y. So they're kind of unrepresentable, well, unmorphism representable vertex set maps, if you like. But anyway, hopefully you can see that this gives you a method of working out all the loops on a particular vertex. I mean, basically, for a given theta, which is in x of l, we can just do these functions on it, find out where it lands, and we can just do the inverse of this, you know, to work out all the loops that go through that vertex, and then we just have to send theta to any one of those loops. So it's this kind of equation here. Right, so blah blah blah, right. This is working out the how the evaluation function works. Okay, so I mean, the evaluation function is going to be a function from y to the power of x times x to y. And so I mean, basically, we think of this as a kind of in two stages. We can either think about the loops or the vertices. Yeah, start by thinking about the loops here. And you can say, well, a loop of y to the power of x times x is going to be a loop of y to the power of x, as in one of these x to y morphisms, basically representing it at least, paired with a loop of x. And essentially, all we do is apply that x to y morphism on that loop of x to get a loop of y. That's basically just how this evaluation function works. Okay, so I mean, we've been really sort of exact about this. We'd say, well, a loop of x is a point of x. A loop of y to the power of x, point of y to the power of x, that technically corresponds to a function from 1 times x to y. But I mean, really, we just think of it as a function from x to y. When we do the evaluation function on this pair, that just corresponds to, taking the anti-adjoint of this sigma here from, this point of the exponential object, taking its anti-adjoint and doing this function on it. So basically, we're just essentially applying this x to y function on x. So we're just seeing how the loops map. So it's the standard kind of idea in exponential objects. The sort of elements from the exponential objects correspond to functions. They get paired with objects to operate on, and the evaluation function just actually operates. On vertices, it's very similar. A vertex of the exponential object corresponds to a vertex map from x to y. That'll be paired with a vertex of x in y to the power of x times x. And all we basically do is apply that map on that vertex to get a vertex of y, okay? Okay, so now we come to the challenging bit, maybe, which is a little bit scary, but it's working out how to work out the adjoint of a working out how to work out the adjoint of a function. Okay, so remember the basic sort of architecture of these exponential objects. We have whenever we have some arrow from z times x to y, there ought to exist this adjoint, g adjoint from z to y to the power of x, which makes this triangle commute here. Okay, just one, in fact. So it's essentially a way to sort of replace the z's here that are, we think of these z's as sort of parameterizing this morphism, if you like, and we want to really replace them. Well, I think the easiest way to explain this is with a picture, actually. So, I mean, this is at least the picture in sets, but in some sense, it's a similar kind of picture in general, just with more kind of associations. But I mean, basically, we have some function g from z times x to y. And so, of course, we can just evaluate that for a given value of z and a given value of y. But the alternative way we like to do it is we sort of, if we're interested in evaluating it for a particular w and a particular v and x, let's say, we can then say, well, let's look at w. Let's look at how this function works on w. And then that'll correspond to a sort of member of this exponential object, sort of like a slice. Okay, and then we can sort of take that function, and then that becomes a member of this exponential object, and it's paired with a and then, if we just take that function, well, say we have a function and a member of x, we keep that member of x alone, keep it the same, leave it alone, and we lift in this function, and then we can just evaluate that function on a particular point on the curve, and it's the same it's an alternative way to find the height above a given point. You know, we can just look directly, or we can slice it and then take it and then look at that curve at a particular point. Okay. So that's the basic idea. Now, so basically this is the important formula in a general kind of pre-sheaf. So what it says is that the way that this exponential adjoint works on a particular value of z, in other words, the kind of well, it's like a function, I suppose, that he wants to represent. Ought to send h of f comma x to where g sends w h of f comma x, where h of f is one of these kind of actions or arrows between Hom functors, and x is an f dash figure of x, and yeah, so the easiest way to understand this is to set h of f to be the identity. At least that's a special case, but it makes a lot more sense, because then you just say, well, all we want to do is we want to send we want GW of u of 1 comma x, which is indeed what we get when evaluating this, to g of w comma x, which is just what you want. So that already shows you that this works, but the other condition is basically so it respects actions. Okay, we also want that. So how does this work in practice? Well, let's suppose we have a loop. All right, here's where it starts. Okay. So, I mean, firstly, it's a good idea to understand how G works. So G's just, firstly, you know, what's this? Z times X. Well, its vertices are going to be pairs of vertices from Z and vertices from X. It's loops, similarly, pairs of loops from Z and pairs of loops from X. What's the vertex of a given loop? Well, just find the vertices of the things in the loop, pair them together. Find the vertices of the two sort of paired loops, and that pair of vertices will be the vertex of the pair of loops in the product. Now, what about an arrow then, G from Z times X to Y? Well, that's just going to map those pairs and shenanigans into you know, stuff in Y. dots and loops in Y. So, okay, let's start to use that formula to work stuff out. So, for a vertex W of Z, we want to work out how this adjoint function works. So, we've got that G adjoint of W is going to be a vertex of y to the power of x. Which one is it going to be? Well, it's basically going to be such that it's going to be this function which basically going to correspond to this function from the vertex set of x to the vertex set of y, which operates on any given v to give g of w of v. So it's like this kind of slice picture I've shown down here. So I mean, this is a bit more explicit. Given a w comma v over here, that gets mapped to a g of w comma v. But the alternative way to do it is to make this function which sort of sends a v to g comma v and then do the evaluation on it. Okay, it's a sort of similar story with the loops. So there's like two ways, like using the simple way of applying this formula, saying h of f to be identity. We get that basically this is going to send a loop w of z to a loop of this exponential object, and that loop's just going to correspond to this morphism, which works on loops just as G works on loops. With this W held fixed. But the other thing, of course, is that for loops, we also want to respect the way that the thing maps vertices. So, I mean, if we take, so we also want this to be such that if we take a point of a loop, and we see how that gets mapped under G, well, we want this loop mapping that this loop's associated with to work on vertices in that way, okay, as well. So that's where this second condition comes from. And I think this h of p here actually just becomes a 1v. Or maybe a p, but I think it's 1v anyway. Then this other question, which is something I've often wondered, we know that the points of an exponential object represent mappings from x to y, and this is generally true in presheaves. In fact, it's true in any category. But the What do the other stuff in the category represent? Well, what about an isolated dot in y to the power of x? What's that represent? Well, it obviously represents a vertex set map from x to y. And it must represent, it must be one that isn't kind of induced by a morphism from x to y. But how do such things come about in practice? Well, it can be the case, as is shown here, that there can be an arrow g from z times x to y, which, if we just look at how that arrow g works on the vertices of x, holding the vertex of y fixed, that corresponds to a vertex set mapping from x to y, and it can be the case that such a thing is not a it doesn't correspond to any morphism. For example, in this case, we multiply x here by a dot, so we sort of turn this loop at 1 here into a dot, and then we can map it to y naught, which is just a bald dot of y. I mean, we wouldn't normally be allowed to, under a morphism, to map a looped dot to a bald dot, but we can when we've done this multiplication. So you're allowed to kind of mess with the structure when stuff's multiplied in ways that do not correspond to morphisms, and that's why the exponential object is not just a load of dots, because it has to have extra structure to represent these extra kind of things you can do. I mean, essentially, this is why this whole idea of it being a kind of parameterized mapping, we have to kind of expand our mind a bit, because you can do more than just the ordinary maps when you multiply by something that's not discrete. And let's finish with something interesting. There's a couple of interesting things, particular cases. So I believe that, well, of course, y to the power of a loop, that's representing the loops in y. I mean, the dots of it are representing loops in y, and it's isomorphic to y, of course it is. This is quite fun. Y to the power of h of v. So a bouquet to the power of a dot, I think this just discretizes it. Because we find that the loops of it correspond to arrows from h of l times h of v, which is just h of v into y, which are just dots of y. So the loops correspond to dots, the dots correspond to dots. I think it's discrete. So if you want to discretize a set, raise it to the power of a dot. I also think, this is a bit confusing, I might be wrong about this, but I also think that when we have x and y are both discrete, then x to the power of y's, or y to the power of x, I should say, is also discrete. I think it all just acts like set in that case. Another very interesting case is when you do x to the power of x. I have to think about the dots here. But certainly loops of this correspond to endomorphisms of X. So we can sort of label them by alpha, comma, beta, and they're actually just morphisms of dynamical systems. Are they? No, not like this. It just looks like a morphism. Well, it's an endomorphism of X, okay? But you can interpret it using a switch as a morphism of dynamical systems. And if you do the special case here where F, as in the loop assignment, or maybe I should call it the vertex assignment, function, when that's just the identity, we find that, so in other words, when X is discrete, X to the power of X is its points, its loops are dynamical systems on its set, its vertex set or its loop set, they're both the same. So we actually find dynamical systems, and we can talk about dynamical systems and morphisms in this case. So then we can talk about things like the Stern-Brockott tree, you know, having its structure like this, 1 over 1, 1 over 2, 2 over 1, 1/3, 2/3, 3 over 2, 3 over 1, and dot, dot, dot. And, you know, we can talk about, for example, morphisms from the Hom functor, you know, representing the natural numbers with counting update function, into this would represent numbers, and we can do all the math we want with that. So, you know, there's this portal into the world of dynamical systems. It's just a very rich and beautiful category, and, you know, it's very interesting to see these connections.